Okay, good evening, Professor David De Los Reyes. Okay, my topic for this session will be area of a right triangle. One of the formulas under geometry is the formula on how to take the area of a right triangle. We know that the area of a right triangle is actually represented by area is equal to 1/2 the base times height. For any right triangle, if this is the base and this is the height, to take the area of the right triangle, okay, it should be 1/2 times base times height, okay. Um, but not all of us, I don't know if all of us know it, that this formula again was derived from integral calculus. It was again derived from integral calculus. So it seems all the formulas that we are using under geometry was derived from integral calculus. Okay. Okay, let's proceed with the emanation of this formula. Why area for a right triangle is actually 1/2 of the base and height. Okay. So I will now be, what we call this, deriving this one by integral calculus. I will make it the simplest one as possible so it will not be boring, okay? If we try to draw the right triangle on the Cartesian coordinate system, this should be the y-axis, x-axis. This is the right triangle, right? The one in orange thing. So if we try to place the coordinates, we must place the coordinates. This point here, we should be with the coordinate. It is at the origin. X is 0, y is 0, so this point here with the coordinates 0, 0. We need this in the calculation of the equation of the hypotenuse because we need the equation of the hypotenuse for us to compute for the area of the right triangle. This point here should be with the coordinates base and 0. This length here is the length of the base of the right triangle. So if we try to specify the coordinates of this point here, this point, it should be small letter b and 0, meaning the abscissa is b and the ordinate is 0. Okay, this is b and its height with respect to the y-axis is 0, so this is b and 0. For this point here, it should be with the coordinates base and its height from with respect to the x-axis is h. So the coordinates of this will be base and h. Why I presented those ones? Because in the computation of the equation of the hypotenuse, which is needed in the computation of the area, we needed those points. Okay. Let's try to compute, okay, or find the equation of the hypotenuse. Because the hypotenuse for a right triangle is actually a variable thing, you know. It's a variable thing. As it moves to the right, it's going up. So it is actually not a horizontal line. It is an inclined line, right? So meaning this line here is a variable line. And we could represent that in terms of x and y. And to represent that in terms of x and y, okay, I will erase this one. I will do like this. By using integral calculus, we put a vertical slice over here. Vertical slice, an increment in differential area. This point here, we should be with coordinates xy. Okay, because we are solving for the equation of this, of y as a function of x. So at this location here, the coordinates will be x and y, and this will be base in h, and this should be base in 0, and this should be 0, 0. We call this angle theta. So to find for the equation of the hypotenuse of y as a function of x, okay, we will use the tangent law. Tangent law, so we go back to trigonometry. If we try to take the tangent of this angle here, okay, Actually, there are two right triangles. The first right triangle is this one. This should be y, right? And this is x. And this is angle theta. The second right triangle will be this total triangle here from 0 to b. So this should be b, and this is x, and this is angle theta. This is theta, this is theta, they're the same. So to find for the equation of the hypotenuse, we use the tangent law. Tangent law, that is now, so actually what I am teaching right now is actually, what they call this, a combination of many subjects. Okay? So we are on the trigonometry at this point, but actually we are also on the analytic geometry side. So taking the tangent of theta will be y over x. Tangent is opposite over adjacent, right? Y over x equal to h over b. And we could erase this one now. So from this equation, we could take the equation of y as a function of x. And y as a function of x is actually y is equal to h over b times x. That is the equation of the hypotenuse. The equation of this is y equal to h over b, right? Multiplied by x. Okay? Also, that's the importance of trigonometry and analytic geometry. Okay? Because we are studying integral now. Integral is a part of, what they call this, there is a trigonometry portion, there is analytic geometry portion. Okay? So we now know the equation of the hypotenuse, and if we try to take for the area, I will erase again this one. I will try to illustrate. Okay, I will try to. The area of the vertical slice is actually this height here times this differential thickness. And this differential thickness is actually dx. And under integral calculus, the area of this one is represented as differential area. It is a differential area. It is only an increment in the area of the right triangle. So differential area, it seems for the meantime it is a rectangle, right? So the area for a rectangle will be length, y, times the thickness. Area for a rectangle, this is dx, this is y. So if we try to take the area, it should be the product of y times dx. So this one emanates from this. Okay? That is the way on how to take the differential area under integral calculus. Okay, I will make it simpler so you will not be bored. So this one here, the next equation emanates from this. Okay, you got it? Okay, I will erase this one so it will look nice. So you now know where this differential area came from. It is the product of dx times y. And if we try to take the integral of both sides, we are now in the integration process. This is now integral calculus. The integral of the differential area will be area, okay? And the integral of the right hand side will be the integral of y dx. But the variables on the right hand side are actually x and y. So for us to integrate the right hand side, we must have to take the relation of y as a function of x. And we already solved for that one. We now know the relation of y in terms of x for a right triangle. So we will substitute. This should be the integral of y, but what is y? It is h over b times x multiplied by dx. H is constant, b, small b is constant, we could bring it out. So it will be h over b, the integral of x dx. We are now on the integral calculus portion. Don't worry, the integration is simple. It is just under the power formula. Okay, let's try to bring out the lower and upper limit. The lower and upper limit, I will show you, it's like this. X here will be 0, x here will be equal to b. This is the differential slice, right? So if we try to take the entire area of the right triangle, this differential area should move or should start from 0, then it will stop at B. So I place it here. The lower limit is 0 and the upper limit is B. Because to take the total area of the right triangle, this differential area should move from 0 to B to get the total area. Okay? So I place it here. The lower limit is 0, the upper limit is B. So proceeding with the integration, instead of indefinite integral, this will now be a definite integral. So this is now definite integration. So this should be h over b. I'm following this. And the integral of x dx, it's under the power formula. It is x squared over 2 with the limit from 0 to b. This is from 0 to b. Okay, we pass by the evaluation of definite integrals. So this is just an easy matter now. This is h over b. We put the upper limit to be b for x. So this will be b squared over 2 minus. The lower limit, it will be a 0 square. Okay, quantity square over 2. But 0 square is 0. And 0 over 2 is actually 0. So this is minus 0. Okay. I will try to erase this one. So what will be next? It's just now a matter of simplification. That is algebra. Okay. So h over b. B squared can be written as a product of b times b all over 2. And actually 1b here cancel with this. So what comes out for the area of a right triangle using integral calculus? Area now will be 1/2 times bh. It is this. Okay, that's it, guys. That is where the area equal to 1/2 bh emanates. It came from integral calculus. Good evening from Los Angeles.